have a quiz due, and this is it. So we do have that due coming Tuesday, and then Thursday your chapter test is due, and we're going to go through section 4.8 today as well. I've got a Kahoot pulled up. If we don't do that today, we'll do it on Tuesday. I like to do that. It's just a way to test review and get a little class involvement, and we can do that solo, so we don't have to be right on top of each other, so that's good. So we'll do that either today or Tuesday. But the first thing I wanted to do was just kind of review these graphing problems. And don't forget, this past Tuesday we did have a quiz due, and most of you turned that in. There are a couple that are missing, so if you did not turn that in, make sure you get that turned in. The makeup quiz is online and available, so please do that as soon as you can. And I do not have those graded yet, but I'm going to probably have those graded over the weekend at some point. So that's kind of where we're at. So the first plot, I'm just trying to think of one off the top of my head. I don't want to give you the same one on the quiz, so you better be careful. Let's use this. Let's say our first plot we want to look at is going to be y equals, well, that does not show up well. Okay, I probably ought to put it on the screen anyway, so let's do that. For our first plot, let's sketch out y equals, I don't know, let's do negative 2 cosine of 2x, and let's just put a -1 on the end. So that's what I want you to plot. I want you to practice plotting by hand this function, negative 2 cosine of 2x -1. So you have an axis you can kind of work with. I'm going to try to put one here on this board as well, if I can. We'll see how it works out. Oh, might work out. And then we'll go over it. But go for it. I'll come around and look around here shortly. That's not what I meant to do. So remember, as I'm grading these too, I am looking for everything to be labeled, including your x-axis. So I'm going to go ahead, I'm going to make mine 2 on here at least. I don't know if I've left enough room, probably not. Oops. Okay, so that looks a little better. So I'm just going to walk around, see how everybody's doing. We'll come back and we'll plot it on the board. this is your question. For those, let's see if I've got some extras here. Two copies. One's the real quiz, one is we're just using the axes to plot. I'll do the same for you, sir. You can use this one to just kind of practice. We're doing some practice plotting, and then do just a copy of your quiz. Somebody's playing Zelda. Alright, so I'm going to, like I said, I'm going to walk around, kind of see how everybody's doing, see if we got some plots coming along here. Our first function is negative 2 cosine of 2x minus 1. Too many plots. Maybe I'll give it another minute or two. Start to draw in some lines and some labels. Oh man, I messed up my drawings there, didn't I? Oops. That's going to be a problem. Be good practice because a lot of you are not. If you plot on the homework, plot online, plotting on by hand is a little tricky. So I guess my first question is, what is the vertical shift? Is there a vertical shift?
It's -1.
It is -1, right? So that -1 tells me everything's going to be shifted down one spot. So what I like to do sometimes is I come in here and just kind of reset myself right here. This is going to be kind of my center line of my graph. So my next question will be, what is the amplitude?
2.
It is 2, right? So that means from that center line, I'm going to be able to go up 1, 2. Oh, I'm sorry, that's not 1, 2. Yeah, it is. And I don't always draw out all these guidelines, but I could also go down 2. So my graph should lie somewhere in that general region. So the next question I might ask is, what's the period?
Pi.
The amplitude we said was 2. The period is 2 pi over b, so in this case 2 pi over 2, which is pi. So my next question would be, I'm probably going to label 1, 2, 3, 4 points on top of 0 here. What would those labels look like?
Half pi, pi, 3 pi halves, 2 pi.
I would say no, not for those labels, right? So if my period is pi, then remember, one of the ways we talked about this, we could come out 1, 2, 3, 4 and make this pi, right? That's one way we could start labeling this. The other way is we could take that period, divide it by 4, and that's going to be the width of each interval between those 2 points, between those points. So if I do that, I get pi over 4. So that means if I start at 0, my next label would be what? Be pi over 4. So then after that would be 2 pi over 4, which is pi halves. Then, 2 pi halves. Then I would have 3 pi over 4, and then I would have pi. So now all my graphs should be between 0 and pi for this cosine function. So I guess the next question is, where do I start? Where's my first point on my graph? Nope.
-2.
It's going to be at -3. All right. So it's not going to be here, because if I started here, that would be sine, right? If I started right here on -1. So that's my center line. It's not a sine graph, so I'm not starting there. So I'm going to start at amplitude. Now in this case, it's -2 cosine. So I'm not going to start up here at 1. I'm going to go down 2, and that's going to be the first point I would plot. I would plot at least, would be right there. Then I would come to pi over 4, and that's going to be up at my center line. So that's going to be right here. And then at my next point, I'm going to be positive up here at this amplitude. And then at 3 pi over 4, I'm back at my center line. And at pi, I'm back down here where I started. Okay, so a single period graph of this should look something like this. Okay, and you could keep going with that if you wanted to, right? If I come over 2 places, this would be a point. And 2 more places, this would be a point. Okay. Okay, so is there questions on that? Concerns with that? Okay, so you've got two axes, so let's do one more graph. Let's do that same thing, but let's plot a different function this time. We'll do a sine this time. Let's try, I don't know, you tell me. You want to do a negative or a positive sign? Positive sign. All right, I'm for it. Let's do 3 sine of let's say pi over 4 x. And that's it. That's your new function. Pi equals 3 times the sine of pi over 4x. So on your second graph, I want you to plot and label that. I'll just try to draw that again. sign and you're trying to get the period, you're taking 2 pi over b. Now, if it was tangent or cotangent, it would be pi over b. So, you're on to this cotangent. It'd be 2 pi over, and what is b? 2 pi over that. You gotta simplify that down. See some pretty good labels. So is there a vertical shift in this one? No. There's nothing being added or subtracted. If I had something like 1 minus 3 sign, would that be an amplitude shift? What would the amplitude shift, or what would the vertical shift be? If it was 1 minus 3 sine pi over 4x? What would your vertical shift be in that case? Say what? Don't be ashamed. Is it? It'd be up or down? I see I have 1 vote for up. Anybody else have a vote? It would be up, right? I'm adding 1 plus 1. Now the sine function would be flipped because it'd now be negative 3 sine, which would be going the opposite way. But that's another way you'll see that written sometimes as 1 minus 3 sine x as opposed to 3 sine of this minus 1. That's a different function, right? Instead of. All right, so no vertical shift. What's your period? So most of you are kind of getting that, looks like. Period would be 2 pi over, in this case, pi over 4. So how do I break that down? Well, that's 2 pi times what? How do you divide fractions?
4 over 5.
Yeah, you'd be 2 pi times the reciprocal of the bottom, so the bottom flipped, so times 4 over pi. So what is that?
8 pi over pi.
8 pi over pi, which is the same, right? The pi's essentially cancel, giving you 8. So how wide should each of these tick marks be in this case then? Say what? I'm sorry. Yeah, I want 4 tick marks to go to 8, essentially, right? So that means if I take period over 4, that's going to tell me how far you don't have to do it this way, but I mean that's a way to measure out how far you want those tick marks to be. So period divided by 4 would be 8 over 4, or 2. So that means for each of those tick marks, I would have 2, and then I would have 4, and I would have 6, and I have 8. So that gives me 5 key points, right, on my graph where I'm going to look at. What's your amplitude? It's 3, right? So 1, 2, 3. I'm going to come up to this bound, and I'm going to go down to this bound. So what's the first point, or a first point, probably the most common first point that you would plot here? 0, 0. It's a sine function, so you're going to start on that center line. Am I going to go up or down? I'm going to go up because it is a sine function. So I'm going to go up to here. And then at 4, where would I be? Back to the center line. What about it? I'm sorry, did that wrong. What about at 6? -3. And then at 8, you're back at your center line. So that kind of gives you those points. Ooh, messed up there. But and you could extend that. You don't have to, but you could extend that. Yes, sir. Where did I get that? Okay, so there's multiple ways to do that, and what I'm really looking for is this point and this point. From here to here, this should be 8, right? Because that is your period. So you can think of that as far, and like I said, there's really 5 key points. Your start point, your end point, and then those 3 points in between. So you could take that 8 and just say, well, what's halfway between there? And that would be 4, right? And well, what's halfway between 4? Well, that would be 2. So that gives me, that 2 is what gives me that clue as to what's really going on. But in all those cases, all you're really doing is taking that period and dividing it by 4, because you're trying to get those, you're trying to basically split this up into 4 sections, because that's kind of your key points. For sine, it's going to be these 5 key points. And for cosine, we saw earlier, it's these 5 key points. Okay. Does that help a little bit? So that's how you split that up. Okay. Any other questions? Okay, so practice this. I do recommend that you kind of learn a little bit how to graph these, not just plot it in Desmos and then try to sketch it out on paper. It's probably better off if you can kind of understand what's going on with these graphs. But that quiz is due on Tuesday, so Tuesday night by midnight or whatever. Your first test is due Thursday, so next Thursday that will be due, and we'll practice that a little bit and get ready. Also, you have the homework assignments that I will collect next Friday. So the day after your test, that next morning at 8 o'clock-ish, I'm going to download all the homework scores for 4.1 through 4.8. So from those scores, you'll either get a bonus of 5 points, or you'll get a deduction of 3 points, or you'll get nothing, right? So but you do need to get 50% or better on each section to avoid any deduction. Okay, so any question on that?
So like we can hit 50 and stop?
You can.
Okay.
Yep. But do keep in mind, especially toward the end of the semester, that at some point those will be average. That'll be part of your homework average, right? So, and you can always fix that too. So, and again, let me know. I believe what has happened is maybe because of the new book that's coming out. But anyway, some of these homeworks have gotten reset. So some of them look, to me at least, like they're quite long. So if they're taking you hours to complete, let me know, and I'll try to get rid of some of the problems. That's okay. I think there's some duplicate type problems in there anyway. We came to one the other day that still kind of threw me for a loop, but that's okay. Where we were looking at plotting I guess an inverse function. Yeah, so you can see my scratch work over there. But. Okay, so all that being said, let's look at section 4.8. We'll come back. We'll probably review some of the 4.7 homework as needed. We did some of that the other day. We did look at some of the 4.7 homework in class quite a bit. So I'm going to skip ahead. And I like this next section. Got some good word problems, applications here. If you think of an application you'd like to see, let me know. I'll throw it in here. I don't know. It doesn't bother me. There are lots of good applications for trig functions. One of those, or a common thing that you're going to maybe use trig for, is to solve triangles. In this section at least, or in this chapter, we're looking at solving right triangles. So when I say to solve a triangle, that means I want to know all the side lengths, and I want to know all 3 angle measures, right? So whether that be degrees or radians is kind of up to you. I kind of like degrees when it comes to application problems, but if you want to use radians, that's fine too, because as you get into calculus, you get into some of the functions that are on here, they're specifically geared for radians. So we'll take a look at that at some point, but it says, all right, solve the triangle seen on the right. So here's our triangle. So I want you to solve the triangle. So I've got some stuff that's given, right? So it looks like I am given at least side A. I'm not given side B yet, so I got to figure that out. And don't have side C. So I have one side, and I have two angles, right? So I have angle A, and I have angle C is a 90-degree angle, right? So the first thing I would say is, hey, if you got two angles, you should be able to find that third angle, because all the angles in a triangle add up to 180. So if I have 90 and 62.7, then my side, or angle B, is going to be 180, and I'm going to subtract from that my other angle measure. So minus 90, obviously, and then minus 62.7. So that's 90 minus 62.7. And that's some number that I'll probably need to go ahead and pull up the calculator. .3 degrees. Okay, now I believe on most of your assignments, when I'm having you find more than one thing, I try to label and say, hey, find this angle, this side, and this side. But here I didn't do that, so I just need to figure out what else do I need to find. I've got A, I got C, I got B now. I got side A, so I got two things left. Got two sides left to find. So somebody pick one. You want to find side B or side C? B? All right. How would we do that? Say what?
Tangent function.
Yeah, probably. Yeah, you can use a function here, right? So I've got some angle measures, and I like tangent because I'm given an angle here. That's given to me, so if I made a mistake finding this angle B, I might be okay still if I using something that is given to me. So if I look at this angle A here, 62.7, and I'm trying to find side length B down here, I've got this given to me, and I've got an opposite side of that angle. So I want to find the adjacent side. So I want to find that. So the way that I can look at 62.7 degrees and say, all right, what relates opposite and adjacent? Well, that's tangent. So I'm going to come in here and I'm going to say, well, the tangent of 62.7 degrees would have to equal what? Well, it'd be opposite, which is 8.4, over B. Okay, so I'm going to find B using this. Fair enough. If you multiply both sides by B, then I'm going to get B times tangent 62.7 degrees equals 8.4. So then you would divide both sides by tangent of 62.7, which could have kind of done this from the get-go, but that's okay. And that's going to cancel then, and I'm going to be left with this. 8.4 divided by the tangent of 62.7 degrees. Well, let's figure that out. 8.4 divided by tangent. I don't know if I can do that in here or not, so I'll just come in here and say function tangent of 62.7 degrees. Make sure your calculator is in degree mode if you're doing that. And I get 4.34. Okay. Any questions on that? Is everybody able to get that? Okay, so how do we find side C? That's the only thing we got left. Pythagorean theorem is probably the easiest. You could do the same thing, right? You could use a sine angle measurement. You could do all kinds of different things. You could pick a different angle to use. For most of you, though, you probably say Pythagorean theorem. So I'm going to say C squared, in this case, would equal 8.4 squared plus what I just found, 4.34 squared. Okay, so let's do that. 8.4 squared is 70.56. I'll just write that in here, why not? Plus 4.34 squared. 4.34 squared is about 18.84. So if I add those together, 18.84, I get about, if I did this correctly, 89.3 or 89.4. Okay, and that's side length C, not angle C. So that's what I get. Do I get anything different? Let's double check using our other method, right? If I'm given this and I'm given 62.7, that's my opposite side. That's my hypotenuse. I would have sine 62.7 degrees equals, and then that side length, 8.4 over C, or in other words, 8.4 divided by the sine of 62.7 should give me C. So let's find that.
Wouldn't we have to take the square root of it?
Yeah.
Oh, yes. Whew. Good call. $9.46. Whew. Glad you caught that. I would have lost points on that. You wouldn't have. All right, 9.46 is your measure there. So let's make sure we get the same thing here, though. Let's see, 8.4 divided by sine 62.7, I think. 9.45. Okay. So I will recommend one thing is that if you're writing down these decimal places like we did here, 70.56, 18.84, I would recommend keeping at least 3, 5, probably 5 decimal places or so if you can. So keep as many decimal places as you can, and then at the end, then worry about rounding and keeping it simpler. Okay, because the homework will do that sometimes, and you'll miss it by 100th or so. So keep as many decimal places as you can feasibly until you get to your final answer, which we didn't do, but okay. So any questions on that? So it's just solving triangles, so you're using those trig relationships, you're using Pythagorean theorem, things like that. So now let's look at one. We've kind of seen one similar to this. It says an engineer sets up a camera 100 feet from the base of the Saturn V rocket in Huntsville to measure the height of the rocket if the camera is positioned 5 feet above the ground, etc., etc. So we've kind of seen one similar to this, I think. So I've got a camera setting up out here, and I've got a little triangle I'm forming here. Now, the first thing I'll say is this camera has it's positioned at 5 feet above the horizontal. All right? So I want to know the height of the rocket. That's what I'm looking for. But here's my camera, and I've kind of positioned it. It looks like 100 feet from the base of the rocket, and I'm measuring up to here. So I've kind of got this triangle here. Looks good. I should probably draw it that way. Sorry. Looking kind of messy, but so I got 100 feet. Here's the base, and it says I am 74.4 degrees. Okay, so I want to figure out the height, so I'm just going to say here height. So if I set this up and I can find the side of this triangle, and I'll call it x. How do I first determine what x is? Okay. First thing I might point out, though, is height is not just going to be x, right? Because that would be the side of the triangle. But I have to add that 5 feet of my camera there. So I'm going to say x plus 5. That's going to give me the height of my rocket. But how do I determine what x is?
Well, first, don't we need an angle of the opposite?
You could get that third angle. You don't have to, because I'm already given 2 angles. And I know this angle, and I know a side length. I would use tangent, right? Because this is my opposite side, x. My adjacent side is given to me. So I already have what I need there to set it up like tangent of 74.4 degrees would be my opposite side, which is x, divided by my adjacent side, which is 100. Okay. Now you could have found this angle, you could have set it up as a cosine type problem, you could do all kinds of things. You could find the hypotenuse. I don't need the hypotenuse, but you could have. So that being said, if I multiply both sides by 100, I'm going to get 100 times the tangent of 74.4 degrees. That's going to give me x. Now, that's not the height of my rocket, but that's x. So let's look at that real quick. Some of you may have been writing, so I apologize. So 100 times tangent, 74.4 degrees, and I get 358.16. Okay, so that's the height of x, but the height of my rocket is going to be that plus 5, right? So it would be 358.16 plus 5 feet. So in this case, 363.16 feet. Okay? Is there any question on that, or how we got to that? All right. Everybody's good so far.
You did have to add that 5 at the end.
Say what?
You did end up having to add the
Yes,
5.
because as we look at our triangle, we're not accounting for that extra height right here, that extra 5 feet of height. So our measurement is from the top of this viewing station here. And the horizontal, we're assuming flat ground, is 100 feet apart. So that part's fine. But the height part, when I do this triangle, I'm only getting the height of this triangle, not this extra 5 feet at the bottom.
Then where did the plus 5 at the beginning? You were waiting
So
to-
this was saying, all right, if I can find x, then I'm going to take x and add 5 to it. So all this tangent 74.4, this allowed me to find x. So then I'm just taking it back up here into the height.
Plugging it into the-
Yep.
okay.
Mhm.
Thank you.
Okay, so next question's a good one. Guy wire attached to the top of the Kermit the Frog float, the Thanksgiving parade, is 102 feet long. So assuming the top of the float flies at 100 feet high, approximate the angle that the wire makes with the ground, or whoever's holding it, I guess we'll say in this case. So this is an interesting problem, and probably the hardest part for most students that I've seen is setting up the problem, setting it up, sketching it out, measuring the right thing. So I got Kermit the Frog here. He's floating along. And he's kind of coming along here, and I've got a guy wire. So here's kind of my direct connection to the ground. And then I've got this guy wire that's coming along. And I'm gonna sketch this out for you because I want you to understand, one, that's going to be a 90-degree angle, just kind of an assumption here. And two, we're going to say that it's to the ground and not to a person holding the guy wire. So we're making some assumptions here. So this guy wire, we're saying, is 102 feet long. And we're saying that distance to the ground is about 100 feet. So what I want to know is this angle. So I'll call it, I don't know, you tell me. Give me a Greek letter that you like to represent this angle. Or not. Theta, alpha, beta, gamma, delta.
Delta.
Delta variant. No, I don't like that. Okay, I'll go with it. So I've got delta here. I want to know delta. Delta usually refers to a change in something, but we'll go with it. So I have delta. How am I going to figure out delta given this triangle though? I would use sine, right? Because opposites of my delta angle here is 100 feet, and the hypotenuse, which is opposite my 90 degrees, that's given to me. So I've given the opposite side and the hypotenuse. So I'm going to say the sine of delta, in this case, is going to equal 100 over 102. Okay? So let's figure out what that is first, I guess. That is 0.98 blah, 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 blah. But I don't want to know that. I know that, well, I'll write that in here. 0.98. How do I then determine what delta is given that equation? What would you do? Say what? What about the decimal? Move it? You could. You don't divide by sign. That's not a bad guess. The sine of some angle equals some decimal place. So if I take the inverse sine of both sides, that's going to give me the angle. And that's what you're doing. When you're taking inverse sine, inverse cosine, you're getting an angle in return for that. So if you take essentially what you're doing is taking the inverse sine of both sides. And that leaves you with delta equals and then whatever your angle is. So if I take the inverse sine of that decimal stuff there, which I just deleted, I get 78.64 degrees. Okay? So is there a question on that one? Okay. All right, so let's move to the next. I like this one. I'm going to let you guys set this one up a little bit. Due to the popularity and domination of Virginia Tech college football, Congress has decided to include a sculpture of the face of Hokie Bird in Mount Rushmore. Designers have decided that on level ground, 800 feet from the base, the angle of elevation from the bottom of the bird to the bottom of the bird, should be 32 degrees, and the angle to the top should be 35 degrees. So first thing I would advise is sketch this out, right? So I've got some camera over here. I'll just draw it this way. So there's one of my angles I'm looking at, the bottom of my bird, and then I'm looking at the top of my bird. Actually, I've changed my mind. I'm going to do this. Close enough. So what would you do here? Tell me. Let's take the first piece of information. The angle of elevation to the bottom of the bird should be 32 degrees. So that tells me from the ground, this angle should be 32 degrees. Is everybody okay with that? Okay. It says the angle to the top should be 35 degrees, right? Okay. So where would you go from there?
Would you make it a triangle from the ground? Looks like a right triangle?
I would do the exact same thing, right? I would say that. I would make that a triangle. Ooh. That's one of the things you can kind of look at.
Is it 800 on the right?
Say what?
Is it 800 on the right?
Now it says on level ground 800 feet from the base of the mountain. So that means from here's the base of the mountain, and I'm measuring from here. So that makes this length 800. Okay. Now usually the tendency is to say, all right, that's 35 degrees, this is 32 degrees, so what's this measure? It is 3 degrees, right? That's 35, 32. You don't need that though, I'll just give you a hint. Because then I'm setting up a triangle that isn't 90 degrees. It's not a 90-degree triangle anymore because that angle right here is not 90 degrees. So let me point out something else. Here's what I want to know. I want to know that height. Correct? What heights, given the information, are there any heights that I can work with?
Base to the top.
Sure, you could go from the base of the mountain to the top of the statue. I can get that length, correct? Let's do that. So if I wanted to do that, this is the length I want. How would you set that up? Tangent, okay. Tangent of what angle? Say what?
35 degrees.
Would be 35 degrees, right? Because that's this angle of this big triangle, this measure is 35 degrees. So the tangent of 35 degrees would have to be what then? I don't know, we'll call it x for our opposite side. And our adjacent side would be 800. Okay, so let's solve that one first. If I multiply both sides by 800, over here they'll cancel, and I'm going to get x to be something. 800 times the tangent of 35 degrees. And I get 560.166. So that's the entire, right? That's this measure. But that's not what I want.
Would you do the tangent of 32?
You would. Absolutely. So if I look at, I can also find this height, right? So if I take this entire height from the base to the top and I subtract out from the base to the bottom, then that's going to leave me with just the height of the statue. So that's exactly right. I'm going to take the tangent of 32 degrees equals, we'll call that y over same base, 800. Figure out what y is. That should be 800 times the tangent of 32 is 499.895. And this is feet. This is feet. So the height that I'm really looking for here should be given by x minus y, right? So if this is your x and this is your y, I'm sorry, that's not x. This is x and that's y, then this part would be x minus y. Does that make sense? Okay, so in this case I have 560.166 minus this answer. So 60.27-ish. Does that make sense? Everybody okay with that? It sounds a little more involved, kind of a neat problem. I don't know. We'll get to some other neat problems. All right, so the next thing I want to introduce is a concept called bearing. And you see this in navigation a lot. You'll see this, and a lot of times if you're looking at a lot of even systems I work with, 0 degrees isn't, x-axis, positive x-axis. It is due north. So that's kind of the 0 degrees in a lot of applications, and that's kind of the same here. So when we're talking about point of bearing, we're going to say, all right, from the origin, and I want to find another point, and that point can be described as either being north or south or up or down. So something degrees, either it's going to be up or down. And then from that vertical axis, you're either going to go to the east or right, or you're going to go to the left, which was west. And the same if it's from the south. So you can see here from this point of origin, this point, you would consider this is 40 north, it's going up, 40 degrees east is where that point would lie. In this case, I'm starting here at the origin, I'm going north 65 degrees to the west. So these are kind of your bearing, lines of bearing, I guess you'd say. The next one, you can see it's below you, so it's going to be south because I'm going down, and it's 70 degrees from that vertical axis. So it's going to be measured from a vertical axis as opposed to the horizontal axis, which is kind of our standard position that we're using. So let's take a look at some examples here. What is the bearing from O to B? So you tell me, what is the bearing, O being the origin here, what is the bearing to point B? It is north, and it is then 30 degrees to the west. Okay. So what about O to C? First question, is it north or south? South, right? It's going down. Then, say what?
20.
It is 20. Very good. 20 degrees west. Now, you're given this 70 degrees, so that means, but off of this vertical axis, remember, that's where we're measuring off of. If this is 70 degrees and this entire quadrant's 90 degrees, so that gives me 20 degrees west. What about O to D? South 20 degrees to the east. Okay, so that's one way that's used to measure. This is an interesting problem here, and it usually, we may not finish it. We may come back to it on Tuesday. We'll finish some other things. But recently, Grover decided to do some hiking on Sesame Street's expansive trail system. He left the entrance and hiked 2.3 miles on a bearing of south 21 degrees west. So I'm going to sketch this out, or try to. So I'm right here. I leave, he goes 2.3, here's his line of bearing, south, 31 degrees, that's east, sorry, west, right, and he went about 2.3 miles, so here's kind of where we're at. It has a measure of 2.3 miles. It says the trail turned 90 degrees clockwise. Right, so he's not going this way anymore. And it says he hiked 3.5 miles on a bearing of north 59 degrees west. So instead of going straight north, he's going north, and then he's going 59 degrees west, and it says he went about 3.5 miles. And we just said that was a 90-degree angle, so that's good. So the next question says, all right, upon arrival at this new point, what was his, how far was he from the entrance to the trail system? And then the second question is, what was his bearing from that? So I guess the first question is how far. So we'll call that C, because this is a right triangle. And I can kind of set that up. How would you set that up? How would you find the length of C? So C squared would equal 3.5 squared plus 2.3 squared. So 3.5 squared plus 2.3 squared. is this number, and just like, so I don't forget from before, I do need to take the square root of that then, and just erased everything I had. So, I get 4.19. Okay, so what's his bearing? You got to find the angles in that case, right? So, okay, how do we do that? Can we do that? Should be able to do it because you got the lengths of the three sides. You should be able to figure out at least all of the angles of this triangle, right? You want to use a tangent function? All right, we can do that. Tangent of what?
2.3 over 3.5.
So the tangent of some angle is going to equal 2.3 over 3.5. And for that to be opposite over adjacent, that's going to be this angle. So I'm going to call it theta. The tangent of theta in this case would have to be 2.3 over 3.5, and we can figure out that angle. If we take the inverse tangent of 2.3 divided by 3.5, we get 33.31 degrees. So that gives us an angle. It's not really a bearing from our original point, but that's okay. So we know theta, and let's call this one alpha. How do we figure out alpha then? You could, but at this point I've got a triangle and I've got two angle measures, right? Say, well, you could use tangent again. I would probably recommend if I have a 90-degree angle and a 33.131 degree angle, I would just subtract those from 180 to get the third angle of your triangle at least. So I would say 180 minus 90 minus 33.31 degrees. That's going to give me that angle. And I get about 56.69 degrees. Okay, so that's alpha. That still doesn't really give me my bearing. How do I determine that? So what I want to know is off of this south line looks like at least. I want to know this measure. Well, I know this measure, and I should have been given that measure, right? That was our original bearing, and it was south 31 degrees west. So I have a 31 degrees, and this angle is 56.69 degrees. So his bearing, well, the measure of that angle would be 56.69 plus that 31 degrees. So that would be 87.69 degrees. So if I said, what's his bearing, what would it be? From the original trail entrance here. South. Yeah, it's south. 87.69 degrees west. Very good. All right, so there you go. You can do some orienteering this weekend, and you can figure out lines of bearing from where you start. So it's kind of interesting. So the next part I'm going to talk about a little bit, and then we'll finish it next week. But really, trigonometric functions are periodic functions because they repeat after a period, right? We talked about the periodicity, and it's 2 pi over b, period is pi over b, whatever. So the period of a given tangent function is pi, right? Sine and cosine is 2 pi. It repeats after that. So those kinds of functions are used to model, I guess, simple harmonic motion and things like the tides and things like that repeat. And in particular, these types of functions are usually represented in a way that looks like this. Sine function or a cosine function, typically, for simple harmonic motion. So here's an example kind of sketched out up here. I have a ball on a spring, and we're making a lot of assumptions here with no resistance, and we're not worried about friction. We're not worried about slowing down. It's just going to repeat forever. So if I looked at the motion, if I pull the ball down on this string here and I let it go, and it was going to go up, and then it's going to come back down, it's going to go back up, come back down, et cetera, et cetera, et cetera. So I could model that using a trig function. So in this example here, at least, if I say, all right, at time 0, I'm right here, and then I let go, I guess the first thing I would ask you is, if I start like this, what kind of function would you use to represent this motion here? Would you use a sine or a cosine? You can. You can use a sine. I would recommend a cosine because I'm starting at the bottom of this amplitude, the bottom of this curve. I'm starting at amplitude. For me, when I see that at the bottom here, I'm going to use a negative cosine function of some sort. Okay? Now, what goes before that cosine? Well, in this case, it's going to be however far I am from the middle distance here. So it's going to be 4, so negative 4. I go 4 down, and then I go 4 up. So negative 4 cosine, and then I have to figure out omega t. So I have to figure out what omega is. Well, that omega, right, if you remember correctly, we said 2 pi over that b, or omega here. That's got to be equal to our period. Well, in this case, I repeat. I get back to my starting point at t equals 6. So in that case, I'm going to say 2 pi over omega is going to equal that 6. So in other words, if I multiply both sides by omega and then divide both sides by 6, I'm really getting 2 pi over 6. That's equal to my omega, and that is the same as pi over 3. So I could make this pi over 3 t. And this function would kind of represent this motion that I've got going on up here with this spring. Okay? Does that make sense? Now, I'm going to use that as the example so I don't get too confusing here. I'm going to make that 6 seconds. That said 4 seconds originally. Okay? So this is the one that's sketched here, so I'll use the same function. But you could be given a problem like this where it's not sketched out for you, and you just reading through this problem. It says the ball and spring is pulled 6 inches below its rest position and then released. So that means I'm starting 6 inches below, or in this case it was 4, and then released. So I'm going to use that negative cosine. The period is 6 seconds, et cetera, et cetera. So we've kind of done one of those. Now, the motion of this type, so as I look at this motion, the number of cycles I complete per unit time, that's considered the frequency. So if you look at here and I say, well, I complete 1 cycle in 6 seconds. So if I think about the opposite of that, it takes me 6 seconds. How many rotations have I done in 1 second? Well, you'd come in here and say, well, it's 1/6 of a cycle. So that would be considered the frequency. So you've probably seen that before in hertz and things like that. So that's kind of where that comes from. Frequency for a sine and cosine is given by this. Omega divided by 2 pi. And it kind of makes sense if you think about 2 pi over b is your kind of frequency, or your period being 2 pi over b, or omega. So it's 1 divided by the period. So we can determine some things. Here's one last problem, and we'll be done for today. An object moves in simple harmonic motion, and here's our function. D equals 12 times the cosine of pi over t, or pi over 4t, where T is measured in seconds and D in centimeters. Find the maximum displacement, frequency, and time required for one cycle. So my first question would be maximum displacement. What's that going to be in this case?
12.
It is 12. It's that amplitude. So it'd be, in this case, 12 centimeters. So next it says find the frequency. And I know frequency, in this case, is going to be omega over 2 pi. So we have to figure out, well, what's omega? Well, this is, again, this part right here is kind of like your B. It's your omega. So I'd say, well, it's going to be pi over 4 divided by 2 pi then. That's going to be your frequency. Okay? So that means what? Well, that means pi over 4 times 1 over 2 pi by fraction math. So I'm going to have the pi's cancel, and I'm going to get 1/8. So the next question is, what's the time required for one cycle? So what do you think?
8 seconds.
It's 8 seconds, right? So I've completed 1/8 of a cycle in 1 second, so that means it's going to take me 8 seconds to do a complete cycle. Or you could say 2 pi over 4 if you wanted to, right? It should be 2 pi times 4 over pi, which is 8 seconds. Yeah. So there you go. You could determine that about radio stations and things like that. Let me take attendance. So stop the video.